Okay, I think we can get started. And so last time we defined the transform, and we start talking about its properties, about its region of convergence ROC. So just like Laplace transform, there are a lot of properties of the ROC of the Z transform, and they basically are mirroring the properties of the ROC of Laplace transform. So we have a 9 property here, and we have 1 extra basically because we break the last property into 2 properties. Okay, so we start with the first property. Says that the ROC of our Z transform consists of rings in Z plane. And we also have this property 1.5 says that a ring is inside the ROC if only if this xn times r to the minus n is absolutely summable. So basically, this thing has has a Fourier transform. So I look at this. So we have a different r, and we will have some r that's inside ROC, means that this Fourier transform of x times r to the minus n converges, and that also means that this xn r to the minus n is absolutely summable. And the condition, so we have a bit of a review slide from chapter 5 says that this is one of the conditions that the Fourier transform exists. Okay, and yeah. Okay, and then we have the next property. Next property says that the ROC does not contain any poles. So this is just exactly like in Laplace transform. ROC should not have pole because by definition at the poles x of z diverges. Then property 3, now we see something different. Okay, so this introduces a major difference between the ROC of Laplace transform and the ROC of Z transform. Okay, so the first part is the same. It says that if x of n is finite duration, then ROC is the entire Z plane. Okay. So this looks the same. So if you are finite duration, the summation always the Z transform summation always converge for all finite Z. But then there are 2 points that's very singular. That's the point of z equal to 0 and the point of z equal to infinity. Okay? So even if x of n is a finite duration, whether the ROC includes z equal to 0 and z equal to infinity is something extra that you need to think about. Okay? So finite value of z, the summation here is just a finite value. But if you want your ROC to include z equal to 0, then you want this upper bound, your summation, to be less than 0, so something like this. Okay? And this is because otherwise, so you just look at this formula, you see that if you have some non-zero coefficient when n is greater than 0, then you have some z to the minus n term. So you have some negative power of z, then those negative power of z will diverge as z go to 0. And so similarly, we want to think about z go to infinity, and you want to ROC to include infinity. That only happens when this n1 is greater or equal to 0. And that's because if if n1 is smaller or equal to 0, then you have some non-zero term. Non-zero term with positive powers of z, and those terms will go to infinity as z go to infinity. Okay? So this is H1 analysis on whether ROC contains 0 and contains infinity. And we go to this example of basically the only function that contain with ROC containing both 0 and infinity is a function that only have a value on n equal to 0, this delta of n. And we see that indeed is the transform is 1, and this thing converge on all the plane. Okay. And then if we do some time shift, now we have this delta of n plus 1. Then we see that the transform is z, and now the ROC doesn't include z equal to infinity, because when z equal to infinity, well, z equal to infinity. And but this ROC still includes 0. Okay. So this is consistent with our analysis here. Okay. So this is a small review, and now we go to the next property. So the next property, we now go to the right-sided sequences. Okay. And if x is a right-sided, x of n is a right-sided sequence, then the ROC will be outside, go to outside infinity. In Laplace transform, we say x of n is right-sided, then x of x, big X of s is also right-sided. But everything now is red bar being a circle, so x of n is right-sided. Then intuitively, then the ROC should go to expand to outside to expand to infinity. And to describe that in mathematics, it says that if some location R0 is some radius R0 is in ROC, then everything bigger than R0 is also inside ROC. And okay, and but but there is a catch, just like in the finite duration case. So the ROC include all finite value outside of R0, but this infinity point might not actually be in ROC, although you think infinity is greater than all the finite value. Okay? And for infinity to be inside ROC, once again, you need to look at your form of your x of n. So say your x of n starts at some n1, then you want this n1 to be greater or equal to 0. Only when that your ROC will include infinity, and that is exactly the same argument here. So if n1 is less than 0, then you have some positive power term, and ROC will not include infinity. Okay, and so once again, we need to look at this upper bound of your this left-sided bound of your right-sided sequence, this n1. And they want n1 to be greater or equal to 0. That's only when ROC will include the infinity. And this case is also kind of special, because you think if x of n is actually h of n is impulse response of something, then this n1 greater or equal to 0 is equivalent to this h of n corresponding is impulse response of a causal system. Okay. So only when your system is causal, its system function, the ROC of the system function will include infinity. Okay, so I guess that's something I should write down. And so this means that H over Z includes infinity if only if a system is causal. Okay, so this is a bit of a spoiler. So this tells us how to determine the causality of a system, of a LTI system. I guess I should say LTI here. Yeah, LTI system is causal. Okay, so that's property 4. Property 4, it also says something about causality. And then we go back to the proof. So we have been saying this outside this thing, and we haven't proved it. And here we don't run through the math, so because we have seen very similar proof in chapter 9, and we just say that by property 1.5, we want something is inside ROC if only if this x of n r to the minus n is absolutely summable. And if you change it from R0 to R1, then this sequence will decay faster. And then because the sequence is bounded on left side, so only way it can diverge is this summation to infinity. But this thing, but this R1 sequence will decay faster than this R0 sequence on the right hand side. So if the R0 sequence is convergent, this R1 sequence must also be convergent, just because it is decay faster to the right hand side. Okay, for increasing n. This is the same logic for the right-sided signal as we have in chapter 9. Okay. And so here has a schematic picture of the ROC of the right side sequence. So the ROC of the right side sequence will be outside some circle and go to infinity, but might or might not include infinity. Okay, and the next property is property 5. So it's for left-sided sequence, and you can propagate for left-sided sequence. The ROC is the other side of the right side sequence, so it's inside of some ring. And mathematically, it says that if some radius is in ROC, then every radius is smaller than that radius inside ROC except for 0. So 0, once again, is a special point, and the ROC includes 0 if only if this upper bound N2 is less or equal to 0. And the reasoning is once again same as the reasoning in property 3.5. And with a picture, and and here we don't even prove this left-sided part. Okay, so this was the left-sided part. The reasoning was same. Now we'll have a signal decaying to. Now we will have a signal decaying to left infinity faster with the radius being smaller, etc. Okay. And so in terms of picture, then this is a schematic of ROC for left-sided signal. So it's inside some circle, and it might or might not include this 0 point. And I guess for here I should mark infinity. So here I should mark infinity point with a question mark. Okay, so infinity might or might not be inside your ROC. And here this 0 point, although it looks very small, it might actually be a pole for your big X of Z. And finally, we have a two-sided function. So if a signal is a two-sided function, then your ROC will be a ring in Z plane. And just like in Laplace transform, the important thing here is there will be only one ring. And the proof is pretty simple. It just says that your two-sided signal, you can pick an arbitrary point to break it into a left-side signal and a right-side signal. and then left side signal has the ROC, right side signal has the ROC, and your ROC of your two-side signal should be the ROC of the intersection of those two. Okay. So you have a left-sided signal, ROC like this, right-sided signal, ROC like this, then their intersection will be most of the time being a donut. Okay. And so let's see an example of this. Yeah, the ROC will be a donut, and then if you are lucky, you might or might not include in 0 and infinity, etc. Okay. And so let's see an example. So we have a signal x of n equal to a to the n from some finite range from 0 to big N minus 1. And with a greater than 0, and x of n is 0 otherwise. So we see that this exactly satisfies property 3. This is a finite duration signal by definition because x of n only has value between this 0 and n minus 1. Now we do calculate the big X of z and try to see its ROC. I guess before we do calculate big X of z, so from here then we can already analyze the ROC of x of n. And because it's a finite duration, so it should include everything except 0 and infinity. And okay, and I guess now we can do voting. So does this thing include does ROC include 0 or infinity? Okay. ROC includes 0 question mark, infinity question mark. Okay. So if you think this includes ROC includes 0, raise your hand. Because people think a little bit. No, if you think it does not include 0, raise your hand. Okay. And if you think it includes infinity, raise your hand. And if you think it does not include infinity, raise your hand. Okay, so people say it includes 0, but not the infinity. Okay, and let's go see. Yeah. Yeah, so this actually includes infinity but not 0. Okay. So yeah, I guess we need some calculation. This is a case where n1 is greater or equal to 0. And I didn't memorize the property myself, so let's see. So we have the condition of we are having this n1 greater or equal to 0. So we are having this containing infinity but not containing 0 case. Okay. So this is a causal case. So in yeah, I guess another memorizing thing is this is a causal case. So this is a causal h of n, and it should include infinity. Okay, so let's go back to our problem. So we know the ROC should include infinity but not 0. But now we try to do this in a bit of a dumber way. So we calculate x of z and see where it converge, and you will see that this makes things very messy. Anyway, so x of z is this summation n from 0 to n big N minus 1, and x of n times z to the minus n. So we have x of n being a to the n, and then z to the minus n. And I guess no, yeah, and now we are making our life be miserable by making some simplification here. And so we look at this, and we see that this is a geometric series because this a to the n, z to the minus n is a z to the minus 1 to the n. And so we use the geometric series formula, so you have 1 minus r to the n over 1 minus r. Okay? And then we try to express this as a rational function of z. Then we then we have z to the minus 1 to the nth power. So multiplying everyone to n, z to the n. Then we have z to the n here minus a to the n. And then here we have a lot of z downstairs. So z to the n minus 1 times z minus a. Okay, so this is our big X of Z. Yeah, and excuse me. Yeah, and then we say that our ROC includes infinity but doesn't include 0. So let's look at infinity. I guess yeah. Then when z go to infinity, then we have basically z to the n over z to the n. So infinity, this thing is 1. So at z equals infinity, this indeed converge. And at 0, then we see that we have a lot of pole here. So we have from here we see a pole of order n-1 at 0 and a pole at order 1 at a. But then we have a lot of weird 0 here. So we have zeros is z to the n minus a to the n has zeros at this circle with radius a. And excuse me, yeah. And anyway, so this pole of order n-1 will give you a lot of pole at 0. So indeed 0 is a pole, and the ROC does not include 0. Okay. And but you want to plot the whole pole 0 plot, then there is something tricky happening. That is there is a pole and 0 cancellation happening at z equal to a, because z equal to a is a pole from this z minus a. But z equal to a is also a 0 from this z to the n minus a to the n, because a to the n minus a to the n is also 0. And so if you try to factor this z to the n minus a to the n, they actually equal to z minus a times this polynomial. And so you see that the z to the z minus a factor will cancel out from this part. So there is actually no 0 or no pole at z to the a, and then there are n-1 zeros on this circle at radius equal to a. Okay. So the remaining zeros are of this form. So they are radius a, and so this zk, and there are n-1 of them indexed by this small k, and they are placed at this equally spacing out point on this circle. So its angle is this 2 pi k divided by n, because there were n points on this circle, and but this k equal to 0 point, which just equal to a, cancel with this z minus a pole. Okay, so pole 0 plot is a bit more complicated. Okay, look at this. Okay. Sorry, and so we actually have a bigger picture on next slide. So here we have we see that we have n-1 order pole at 0, and there are also n-1 different zeros on this circle of radius a. Okay. And this is a schematic plot for a less than 1. So a is inside this circle, is inside unit circle. Okay. And let's see the next question. And we have x of n equal to b to the absolute value of n, with b greater than 0. And this is a two-sided sequence. And here the value of b will be pretty important. And so if b is less than 0, then this thing is actually decaying when absolute value of n is getting bigger. So it looks like this is a two-sided decaying function. And when b is greater than 1, then this thing is exponential growing with when n is growing. So we have this two-sided exponential growing function. And from here, you can probably already feel that this thing is much more stable. This is much more unstable, and summation here is a lot harder to converge. And anyway, so x of n is a two-sided signal looking like this or this. Now we want to see what is ROC. So we do what our property says. We want to break it into a left-sided signal and a right-sided signal. And a good point to break those two signals is at equal to 0. So you look at the exponential decay on this side and the exponential decay on this side, etc. So break it equal to 0, then you have x of n equal to this b to the n u of n. This is when n greater than 0. Then you have b to the minus n u of minus n minus 1. This is for n less than 0. And then we can do, I will need a extra spacing here. We can do, well, we haven't said about how to do inverse Fourier transform, but those two signals we already seen is, never mind, sorry, I got confused. Okay, so those two signals we already do the Fourier Laplace transform. Yeah, so those two signals we already do the transform in example 10.1 and example 10.2. And this is our favorite exponential signal. So it's this transform is 1 over 1 minus bz minus 1. And with ROC being greater or equal to b, radius greater or equal to b. And the other signal, it doesn't look exactly the same, but actually a special form of this minus a to the n u of minus 1. And so we just need an extra minus sign to cancel this minus sign. And also with b equal to, with a equal to 1 over b. So you z transform, then this will become minus 1, this minus sign from this minus sign, and over 1 minus b minus 1, z minus 1. And this minus 1 from a equal to 1 over b. And for this thing, the ROC will be inside, will be z is inside, this a equal to 1 over b. Okay, so we have the right-sided part being the transform to this thing, and the left-sided part is transformed to this thing. And now we want to see its overlap. I guess I should change the order. Okay, and it's easier to see graphic and to see those in graphic. And now we need to analyze the two cases, whether b is greater or equal to 1 or b is less than 1. And so we have those two z transform. And if b is b is less than 1, then we have that the first signal ROC look like this, because b is less than 1, and ROC is greater than is less than 1b. And if b is less than 1, then the second signal ROC look like this. And so you think about the overlap between this shaded region and this shaded region, then you see the ROC is this ring between b and 1 over b. And whereas if b is greater or equal to 1, then the first ROC, then the first signal ROC is this shaded area outside of unit circle, and then the second ROC is inside this unit circle, this shaded area, and you see they have no overlap. And so in fact, when b is greater or equal to 1, you cannot have both those two signals converge, and there is no ROC, and x of z doesn't exist anywhere. Okay. So when b is greater or equal to 1, we don't have any ROC, we basically don't have x of z. And when ROC is when b is less than 1, then we have this overlapping ROC. So we have a z between b and 1 over b. And x of z, you can write everything together into this rational function of z. Okay. And yeah, that's what happened. Okay, and so this is the double-sided exponential signal, and this example to lead us to see through this two-sided signal analysis, where we have a left-sided signal, right-sided signal, and we see that they have their own ROC, and the overlapping between those two ROC will be the ROC of the resulting signal. Okay. And finally, we have this three property. And property 7, just like Laplace transform, says that If the signal is rational, then the ROC are bounded by poles or extend to infinity. And we don't directly prove this, but yeah, we just state it here. And then property 8 and 9, as we say, was basically the old property 8 breaking into two parts because now it's very long because we need to say something about 0 and infinity. Okay, and property 8, well, it was combining property 7 with the previous property. It says that if our x of z is rational and x of n is right-sided, then ROC will be outside. So from right-sided, your ROC will be from outside, and then from rational, your ROC should start from some pole. So if you are both rational and then right-sided, then ROC is outside of the almost pole. But then there is a caveat. You need to take extra careful about this z equal to infinity. So so ROC include infinity if only if well, here we have a weird saying, but we say x of n is causal. Okay, so basically if x of n is 0 for n less than 0. Okay, here this is a bit of abuse of notation because is a bit of abuse of notation because system is causal, and here we are saying a signal is causal. But what we actually mean is that if the signal is an impulse response of some system, then that system is causal. Okay. Anyway, so yeah, so that's the condition for ROC also including infinity. And similarly for property 9, if our x of z is rational and its time domain function is left-sided, then ROC is inside the inner pole as a non-zero pole. Okay, so we don't count the zero pole. And also whether z equal to 0 is inside ROC is something actually you need to calculate. And your ROC includes z equal to 0 if only if your signal is here. Once again we abuse the notation. We say the signal is anti-causal, and what we mean is that x of n is 0 for n greater than 0. Okay, everyone okay with those all 9 properties? Well, okay, then let's go see more example. So yeah, let's determine all the possible ROC with this function. This z transform. So big X of z equal to 1 over 1 minus 1 over 3 z minus 1 times 1 minus 2 z minus 1. Yeah. And then okay, so we can determine ROC by just look at the pole 0 plot. Okay. And so if we multiply, it's a bit more tricky. So for poles from those two terms, you can see that z equal to 1 over 3 and z equal to 2 are 2 poles just from those two terms. But because of there are a lot of different z minus 1, so actually there are double 0 and there are 2 zeros at z equal to 0. Okay. And yeah, so 2 zeros at z equal to 0 and pole at z equal to 1 over 3 and pole at z equal to 2. And we can determine ROC, so this is quite like a Laplace transform. So we can determine ROC by using property 7. Okay. So this is a rational function of z, so that the ROC should be bounded by the poles here, and then the 3 possible ROC is outside. So there are only 2 non-zero poles here. So the 3 possible ROC is outside of the outermost pole, or between those 2 poles, or inside the innermost pole. Yeah. So yeah, so the 3 possible ROC is pretty easy to figure out. It's those 3 things. and we can do a bit of analysis of the associated signal for those three ROC. So for this outsidemost ROC, then because we know the ROC is outside the outermost pole, is expanding ROC, then the signal must be right-sided. And similarly for this ROC is inside the innermost pole, so the signal should be left-sided. And then for this middle ROC is neither inward nor too extending, so the x of n is two-sided. But this ROC also has some nice property is that this ROC includes this unit circle, and yeah, so this ROC include a unit circle, and so the signal will have a Fourier transform. And also a bit of a spoiler, this also means that the system function correspond to a stable system. Okay. Yeah. So ROC include a unit circle, and this means that the time domain signal will have a convergent Fourier transform. Okay. Well, good with the properties of ROC. If so, then let's go to the next topic. The next topic is the inverse Z transform. And in this section, we actually have something extra from the Laplace transform. Okay, so there are basically three methods to do inverse Z transform. And the first two methods has a corresponding Laplace transform part. So first method is just do integration, brute force integration from the formula, just like some kind of integration you do in Fourier transform. And then method 2 is when you have a rational function, you can do this partial fraction expansion and just look up the table to do inverse Z transform on each partial fraction. And obviously you need to take care carefully look at your ROC to decide which inverse Z transform you want to do. And then there are actually kind of funny in method 3, that is power series. We'll see very soon. That's because the Z transform actually has a very nice power series expression always. So sometimes if your big S of Z is in a power series, then you can just look at your big S of Z to determine your X of N directly. Okay. And so we have two sub-methods that just is used to that you can use to write your Z transform, to write your big X of Z as a power series. Okay. So those are our three methods, and let's start with the derivation of first method. So first method, we do integration, and basically we want to use the inverse Fourier transform equation here. So we start with big X on some R, and e to the j omega is the Fourier transform of big X on some R, and e to the j omega is the Fourier transform of X of N R to the minus N. Okay. And this only happens when your R is inside ROC. And you can apply inverse Fourier transform on both sides, and so inverse Fourier transform on this side become Xn R to the minus N, and that's equal to inverse Fourier transform of big X R e to the j omega. Okay, and excuse me, and then we move things around. So we move this R to the minus N to the other side. So we have X of N equal to R to N inverse Fourier transform of your big X on R e to the j omega. Yeah, so we basically fix an R here. Fix an R here inside the ROC, and now we just write down the inverse Fourier transform formula. Inverse Fourier transform formula is integration on omega. So omega will be from some 2 pi interval, doesn't really matter. So usually it's from 0 to 2 pi, and our big S of R e to the j omega, and times e to the j omega. then d omega, and also with a 1 over 2 pi. So from here to here, we just write down the inverse Fourier transform formula that we had in chapter 5. It is 1 over 2 pi integration big X times e to the j omega and then d omega. Okay. And I guess from those points, we consider, we should say here, so we basically consider fixed R. Consider fixed R. Okay, so R is some constant fixed inside ROC, and we can do all those integration. And so this is a very well-defined integration you can do. This is basically same as the inverse Fourier transform integration you can do in chapter 5. This is an integration of d omega, and this is some periodic function of omega, and you can pick the favorite 2 pi interval you want to do this integration. Okay. So if we fix some R inside ROC, then this is the integration you can do. And but we want to make this more formal, just like in chapter 9. And we say then we move this R to the n inside, and so this become R times e to the j omega to the n. And now we think this yeah. So we are yeah. So here we have R fixed. And from this inside, then we want to change the integration from d omega to dz, because we are thinking we are integrating on some contour in the z plane. Okay, so we want to change the variable integration from omega to z, and z was equal to r e to the j omega. So dz will equal to, so we do this small differential calculation. So dz with r fixed, dz equal to then your differentiation on this omega, so you get hrj here. So jr then e to the j omega and d omega. Okay. And then we want to express everything in z, so this r e to the j omega becomes z, so dz is just j z d omega. Okay. And move things around, because what we actually want is express this d omega as dz, so d omega equal to dz divided by this j omega, so divided by this jz, so 1 over jz minus 1. Okay. And with all those things together, so we substitute this d omega back into this equation, and say this r e to j omega equal to z. Then everything together, we have x of n is 1 over 2 pi j, and integration of something, integration of some contour inside ROC with a circle, and or x of z. So x of z from here, then z to n minus 1, because it was z to n, then multiplying with z minus 1 and dz. Okay. So this is a contour integral you can do to get your inverse z transform. And we have this weird circle sign, means that we are integrating over a counterclockwise contour inside our ROC. Okay. And once again, the radius r can be anything inside ROC. This should give you the same value by the complex analysis theorem. And in fact, this contour don't even need to be a precise circle, even though we derive this for some fixed r. So this contour should just be some closed circle inside your ROC. Okay. And yeah, so this is the contour integral, and here we have some other formula for comparison. So this is the inverse z transform contour integral, and here we also have the inverse Laplace transform contour integral here. You see it's quite similar. You have those 1 over 2 pi j. And then here we have the z transform formula and the Laplace transform formula for comparison. Okay, so this is method 1. You can do integration. In this contour integral is be more complicated. Although if you do more complex analysis, then this is actually has some easy way to do by analyzing the poles inside. But if you really want brute force calculation, then you can run this formula with some fixed R. Okay, so that's the integration. Then there is a partial fraction expansion. So we try to, but now partial fraction expansion is also more complicated. Okay, because basically because example 10.1 and 10.2 are more complicated. Particular example 10.1 has this z minus 1 in it. Okay, and anyway, so we have some example here as example here to show how this works out. So we have x of z equal to, so everything is actually a polynomial in this z minus 1. So we have 3 minus 5 over 6 z minus 1 over 1 minus 1 over 4 z minus 1 times 1 minus 1 over 3 z minus 1, and with the ROC being z greater or equal to 1 over 3. And this thing has a pole at 1 over 4 and a pole at 1 over 3. And it has a whole bunch of zeros, but let's ignore zeros for now. Okay, because the poles are more important here. Okay, so it has a pole at 1 over 3 and 1 over 4, and we have ROC being outside of this 1 over 3. Okay. And now we want to do partial fraction expansion to do the inverse of the transform. So we actually expand in z minus 1. Okay, so we want to express in a polynomial of z minus 1. And when you do, and we see that here we already write this as a rational function of z minus 1. So you can easily expand this as a polynomial in z minus 1 to get x of z equal to this 1 over 1 minus 1 over 4 z minus 1 plus 2 over 1 minus 1 over 3 z minus 1. And once again, we skip all the calculation of partial fraction expansion. Okay, hopefully we can do this. For this example, this is quite straightforward. We just expand in terms of z minus 1. Okay, and now we have those two terms, and we want to do inversely transform. And this thing has a pole at 1 over 4, and this thing has a pole at 1 over 3. And we want to see what's the corresponding ROC when we do the inverse transform of them. Okay, and so we have x of n equal to x1 of n plus x2 of n, x1 of n equal to this, x2 of n equal to this. And we want to determine the ROC. And just like in Laplace transform, now we see the ROC was outside of both poles. So the ROC for them must be both be the outside. So ROC for them should be greater than 1 over 4 and greater than 1 over 3. Okay, and then with those two, then we can run example 10.1. Example 10.1 says that if you have an exponential decaying signal, then the z transform will look like those two things, and so inversely transform to those exponential decaying signal. So we have a equal to 1 over 4 here, and a equal to 1 over 3 here, and also extra 2 here. Then finally, with linear combination and back, then we have x of n equal to 1 over 4 to n u of n plus 2 times 1 over 3 to n u of n. Okay. So this is a partial fraction expansion. Okay, and we're okay. And so this is very similar to Laplace transform, and similarly to Laplace transform, we can have 3 different inverse z transform for this algebraic part. So now, why do I copy paste the 2 cents in here? Anyway, so we have this algebraic expression, and now we want to see its inversely transform for this middle ROC, so ROC between 1 over 4 and 1 over 3. And then we have the same partial fraction expansion, so we already, so we write the partial fraction expansion here. and the ROC was between 1/4 and 1/3. So now the ROC is outside of this 1/4, but the inside of this 1/3. So the corresponding ROC will be greater or equal to 1/4 and greater than 1/4 and less than 1/3. So the greater than 1/4 ROC, greater 1/4 signal still give you this right-sided signal with example 10.1. This is exponential decay 1/4 to the n. And for this less than 1/3 signal, then we need to use example 10.2. And it will inverse transform to this minus a to the n u of minus 1. And so a was 1/3, and so small x2 will be the signal. So x of n will be small x1 plus small x2 and become the signal 1/4 to the n u of n minus 2, 1/3 to the n u of n minus 1. And finally, we have the third possible ROC being z less than 1/4. And now the ROC is inside of both poles, and both of those partial fraction will inversely transform to a left-side signal. So both of them will be this minus a to n u of minus n minus 1, and so our x of n will inversely transform to this minus 1/4 to the n u of minus n minus 1 minus 2 1/3 to the n u of minus n minus 1. And we can generalize a little bit of this to a lot of rational functions. So if our rational functions can be written in this single poles in terms of z minus 1, linear terms of this z minus 1 term, then we already see how to do the inversely transform. Okay. So if x of z is a linear combination of 1 over 1 minus a z minus 1. So basically we do a partial fraction expansion in terms of z minus 1, and if every term is order 1, then we know how to do inversely transform, because those terms has pole at z equal to a, and then if ROC is outside a, then you inversely transform to a to n u of n, and if ROC is inside your z of a, then you inversely transform to minus a to n u of minus n minus 1, and then just a linear combination and back. And then once again, for higher order poles, then you need to be more careful about your z transform. You need to first derive the higher order formula, and you need to derive the higher order formula, and then you by the differential property, and then also do your partial fraction expansion more carefully. Okay, sorry for going over time, and we will take a 10-minute break and start our method 3. Okay, let's get back. And let's talk about method 3, the power series expansion. And the idea of the power series expansion is very easy, very simple. So basically, we look at this z transform equation. So it says big X over z equals this summation n from minus infinity to plus infinity x over z to the minus n. And we see that this is a power series. So we have a different power of z here. This is z to the minus n, and n from minus infinity to plus infinity. So if our x over z was already in this form, then we can just look at this and read into the corresponding x over. Okay. So if our x of z is already in this form, then we can just read from it what the x of n is, and if it's not, then we can try to express it into this form and get the x of n from this expression. Okay. So let's see some example of this. So first we have our x of z equal to this 4z squared plus 2 plus 3z minus 1, and with ROC between 0 to infinity. Yeah. So we have because all those things are pretty convergent, so our ROC is just a very large range. Okay. And so we compare this thing to this thing, and so we see this 4z squared term is equal to n equal to minus 2, and so is equal to n equal to minus 2 with x over n equal to 4. And then this 2 term is equal to n equal to 0 term with x equal to 2. And then this 3, the minus 1 term is equal to n equal to 1 term with x equal to 3. And then we have no other term. Then we see that if our x over n is just this thing, then we will, by this formula, we'll get x over z that look like this. Okay, so this is just basically we see that if our x over z is already in a power series, then we can get our x over n by inspection. And so if we want to write this thing into a more complicated equation, then we write x of n equal to 4 times the delta of n minus 2. So it has a 4 at n minus 2, then it's 2 times delta of n, 2 at n equal to 0, plus 3 times delta of n minus 1. So 3 at n equal to 1. So this is how we write down this. And another way to see this is we note that there is a z transform between z to the n0 and delta of n plus n0. So every z to n0 you just transform to delta n plus n0. So you see that you have z to the 2 here, then this inverse z transform to delta of n plus 2. And z to a 0 here, the inverse z transform to delta, then delta of n, and this z to the minus 1 term, inverse z transform to delta of n minus 1. Okay. So this is very simple. You look at this equation, then you can immediately write down your x over n. Okay. And now let's talk about a more complicated case. And this is a case where where the ROC actually play a role. So we have our x of z equal to this 1 over 1 minus a times z minus 1, with ROC being outside of this a. And this example, we already know how to do inverse z transform because this is the example 10.1. But let's try to express this as a power series. So what we do is we do long division. So we try to divide 1 by this 1 minus a z minus 1. And you see that this is 1 plus a z minus 1 plus a squared z minus 2 plus dot dot dot. Yeah. Because this is just what happens when you do long division. because you subtract 1 minus az minus 1 from it, then you get az minus 1, then you subtract az minus 1 times 1 minus az minus 1 from it, you get a squared z minus 2, etc. So you get a power series in terms of az minus 1. Okay. And then here the ROC is important because we have that absolute value of z greater than absolute value of a, so this power series expansion is convergent and it makes sense. Okay. Because each term gets smaller and smaller in absolute value. Okay. 1 plus az minus 1 plus a squared z minus 2 plus dot dot dot. Okay. And yeah, as we said. And then from here, so you compare this to this formula, then you see our x of n will be 0 for n less than 0 and equal to a to the n for n greater than equal to 0. So you see that for n equal to 0, x of n equal to 1, for a equal to 1, x over 1, sorry, for n equal to 1, then x of 1 equal to this a, and when n equal to 2, x of 2 equal to a squared. So you see that the x of n equal to a to the n times u of n. And this is same as our example 10.1 calculation. Okay, and so basically you can also so if you remember what we do in example 10.1, what we do is basically we reverse the calculation of example 10.1. Example 10.1 we say our x of n was this thing, then we use this formula to get that the big Z was this geometric series summation, and the geometric series summing over sum to this. So basically this long division, what we are doing is we are inversing the geometric series summation by doing this long division. Okay, and so then the next example is a similar example. So basically we are reversing example 10.2. So we have the same. So we have the same algebraic expression, but with a different ROC. Now we have big Z. We have the absolute value of Z less than absolute value of A, which means the absolute value of Z minus 1 is greater than 1. Then the previous long division will give us a divergent power series. So this is not the correct expression and not the correct expansion. And we want to do the power series expansion in other direction. So we divide this one with, so we write this minus az minus 1 at the front and as the first term, and this plus 1 as the second term. Okay, so we try to match this a minus 1, because now we think az minus 1 is greater than 1. So this is the first term and this is the second term. And we try to expand in terms of the negative power of this thing. Okay. And so indeed we do division. So we said we want to set 1 equal to this minus az minus 1. So we need to multiply by 1 over this thing. So that's minus a minus 1z. And minus a minus 1z multiplied by this thing is, so those two things multiplied together, indeed you get a 1 here. And you get a minus a minus 1z. And so you get a leftover a to the minus 1z, and then once again you try to match this a minus 1z with this minus a z minus 1, so you get a minus a minus 2 z2. Okay? And then you can see the trend is you keep subtracting powers of this a minus 1z. Okay, so this is minus a minus 1z, minus a minus 2z squared, minus a minus 3z cubed, etc. And now this long division will get turns smaller and smaller because each term has absolute value less than 1. Okay. And then once again, then you look at this formula and you try to determine x of n. Then you see x of n is 0 for n greater or equal to 0 because you only get positive powers of z. And from this first term, you get x of minus 1 equal to minus a minus 1, and x of minus 2 equal to this minus a minus 2, etc. And x of n will just equal to minus a to the n u of x of n will just equal to a to the n u of minus n minus 1. And that's consistent with our example 10.2. Okay, and finally, let's see even more complicated example of we do power series expansion to do the transform of more complicated formula. So, so if we have kind of whatever z, then we can just if we have whatever x of z, then we can just do Taylor expansion or power series expansion, and to write it as some so write x of z as expanded some point z0. This is just excuse me. This is just calculus. Calculus says that if you have a smooth function, then you can expand it at some points to get that x of z equal to this expansion point x over z0, then plus those corrections with the derivatives of big X at z0. So big X to the nth order derivative at z0 divided by n factorial and times how far away you are from this z0, this is z minus 0 to the nth power. And then you sum over all those correction terms from equal to 1 to infinity. This is the Taylor series expansion. And this is nice because we can do this expansion even for non-rational z transform. So even if you have a non-rational big X of z, then you can try this power series expansion, Taylor expansion, to get it into a power series of z. And then usually the best z to choose here is you want to pick z0 equal to 0. Because you pick a z0 equal to 0, then you just have a constant term here, and then you have powers over z. And yeah, and you see that here we want the powers of z. Okay, and that's usually, and let's see how this works out. Yeah. That's an ideal case, but we see that in our case we pick a bit of a different expansion, and it's a bit smarter. Okay, and anyway, so now our x of z is indeed a non-trivial function. We have this weird function log 1 plus a z minus 1. Okay, with non-trivial ROC of big Z greater than, absolute value of Z greater than A. Okay. And now we want to do power series expansion of this. And what we do is we don't expand with, excuse me, we don't expand in terms of Z because this is too ugly in terms of Z. Okay, so we actually expand in terms of this AZ minus 1. Okay. So I guess I should write that here. So we have we define some new. I guess sorry, this is actually v. So if we define this v equal to this az minus 1, and this is nice because we know az minus 1 is small, so we are expanding. At least it's less than 1, so we are expanding on something that's not too big. So with calculus, we know that log of 1 plus v equal to summation n from 1 to infinity minus 1 to the n plus 1, and this is v to the n over n. And this happens when v is less than 1. And if you want to check the calculus, this is the page. Okay, so you can do derivative of this signal, this function at v equal to around v equal to 0. Okay, and so you have its derivative will be 1 over derivative of log x is 1 over x, etc. And yeah, I guess you can check all this, and you can check all those order. Sorry, I guess we can check the easiest term, right? So the zeroth order term is x of z0. So at lowest order term, x of z0. So we are expanding this log of 1 plus v at v equal to 0. So this is the Taylor expansion at v equal to 0. Okay, so then the first term is this log of 1 plus 0, then it's just 0. This is the x of z0 term. Then you have the higher order derivative terms, and there will be this 1 and minus 1 factorial, and 2 factorial, minus 3 factorial, etc. And so this this upper term this minus 1 to the n plus 1 comes from those derivatives, and then this factorial kind of disappear because they cancel. The factorial disappear, it becomes just this n, because then there are those n minus 1 factorial here, etc. And anyway, let's don't go into too much detail of the calculus. So by calculus, you can get this expansion formula of log of 1 plus v. Expand at 1 v equal to 0, we'll get this Taylor series of minus 1 to the n plus 1, v to the n over n. And this expansion will work for v less than 1. And that is consistent with our az minus 1 is less than 1. And then you apply v equal to az minus 1 into this, then you get our x of z expanded as the power of az minus 1 is the summation n from 1 to infinity, minus 1 to the n plus 1 from here, and you basically just subtract this v to az minus 1, so this is a to the n, z to the minus n. Okay, so then with this formula, this is once again a power series of z. Okay. And so with this power series of z, then we see that our x of n is, well, now we only have negative powers of z, so it's 0 for n less than equal to 0. And with positive n, then we have our x of n equal to all the other thing other than z to the minus n, is minus 1 to the n plus 1 times a to the n over n. Okay. So our x of n will be equal to this minus a to the n over n times u over minus 1. Okay. Everyone okay with this? So this is a quite complicated example. I guess this is not quite straightforward, because you need to identify that you want to expand with this az minus 1. So I guess this usually part is not quite correct. Sorry, let's close all this. And yeah, so this power series expansion and all those long division stuff, you need to be a bit smarter about what you are dividing and what you are expanding. But when you do things correctly, then the ROC will fit, so your expansion. So if you choose correctly, then your expansion will have a convergence radius fitting with your ROC, so your expansion is valid. And hopefully you expand into powers of z, and then you can directly look into the formula to determine your x of n. Okay. We have about 30 minutes, so I think we can go over a little more. So we can talk about geometric evaluation of Fourier transform from the pole zero plot. So this is very similar to what we've in Laplace transform case. So we know that Lie transform is Fourier transform when z equal to 1. And also for rational function, the value of the transform is basically determined by the location of the zero and the poles. So we can determine the value of a Fourier transform by just looking at how close you are to each zero or pole. Okay. And so basically here we just go straight into example. So we have first order system. We didn't actually talk about what's first order system, but anyway, it's a system with this kind of impulse response. Okay, and its impulse response is our very familiar function. It's a to n u of n. Okay, so we have a causal first order system. You will have this impulse response, and anyway, let's analyze how the Fourier transform of the thing will look like by looking at its Z transform. So Z transform we know is 1 over 1 minus A times Z minus 1. And if you want to write this in terms of a rational function of Z, then it's Z over Z minus A. Okay. And the ROC will be greater or equal to A. Okay. And if you want to have a Fourier transform, then A should be less than 1. And so the ROC will include a unit circle. And in that case, the frequency response will be this thing with z set to e to the j omega. Okay, so it's this 1 over 1 minus A times e to the minus j omega. Okay. And so we can think about what's the amplitude and phase of this thing by looking at a picture. Okay. And we look at a picture and we plot the point 0 of this thing. So this thing has 0 at 0 and a pole at A. Okay. And as we said, the Fourier transform will be the value of the Z transform. Okay, so 0 at 0 and a pole at A. And the Fourier transform will be the value of this signal, this function on this unit circle. Okay. So you change the angle here, the angle will be omega. So you can change omega from 0 to 2 pi, and then this will be a periodic function with period 2 pi, so we back to sin equal to j omega. Okay. And yeah, so there is a pole here and a 0 here. So basically your distance to 0 doesn't change when you work on this circle. And so the amplitude only depends on your distance to this pole here, and the closer you are to this pole, the higher your amplitude is. So around angle equal to 0, you have the highest value. You have a peak around omega equal to 0, so you get those peak here. And also when your A is closer to 0, then you are peaking higher, because then this D minus A will be smaller. Okay, so here we have a small a equal to, okay, so this is quite small. Okay, so A equal to 0. I guess it's actually larger A. So A equal to 0.95A, then you have a much higher peak, and A equal to 0.5, you have a smaller peak. And so it's easier to see the amplitude, and we can also analyze the phase. So the phase will be, so if you want to analyze the phase, then you need to subtract the phase from the numerator and the phase from denominator. And basically when you work a full circle, then this angle on this 0 term will come from 0 to 2 pi, and then the angle with respect to this point A will also come from 0 to 2 pi. So we go from full circle, then the angle doesn't change. But on some point you have a larger difference in the angle, and on some point you have a smaller difference in angle, and yeah, and the difference change faster around omega equal to 0, and you have a different peak for different value of A. So if A is So if a equal to 0.5, so this point is further away from this 1 point, then the change in phase is smaller. And if a is closer here, I guess we can get a bit of intuition here. So if a is very close to this point, then as your omega change from 0 to some non-zero value, you quickly get non-zero omega 2 here. Okay? So because the angle with respect to your a will be very fast, will be very large. Okay. Let's try to draw here. So if your a is close to here, and if your a, let's draw a very big circle here. Okay. If you have this is a slice of very big circle, and your a is here, and you think about you have some omega point here. Okay, so you just change it to some small omega. Then this angle between this angle from a to your e to a j omega point will be very large. Okay, and that's why when our a was 0.95, the angle changed a lot around this omega equal to 0 point. Okay. And yeah, so that's geometric analysis. This is an example of a geometric analysis you can do on your Fourier transform by knowing the zero and the poles of your Laplace transform. And I think it will be early, but we are okay with our schedule, so we'll stop early today. Okay. And I think we have covered enough. Let's do a small recap. So today we go over all the properties about ROC. So we finish those properties about ROC of our Z transform. Okay, so yeah, so properties of ROC. Property 1, the ROC the point with where x of n to the mass n is absolutely insummable, and then ROC doesn't contain poles. And for finite duration signal, ROC is everything, but except if you want to include this z equal to 0 point, then your signal should be 0 when z is greater than 0. And if you do if you do abuse of notation, this means your x of n is anti-causal, and I guess I shouldn't say that. Sorry. So x of n is impulse response of anti-causal system. And also, if your ROC want to include z equal to infinity, then your x of n should be impulse response of causal system. So it's 0 when n less than 0. And then we have the right-sided and the left-sided equivalence. So if you have a right-sided sequence, ROC is the outside of a ring, and ROC is the outside of a ring, and you want to include the infinity point, then your x of n should be 0 when n less than 0. And left-sided is similar, so it's like this. And left-sided is similar. If your signal is left-sided, ROC is inward, but they include 0 if only if it's 0 when it's greater than 0. So ROC can look like this, and it might not include 0. And if you have a two-sided signal, then your ROC will basically be a ring or a donut. And yeah. Okay, and we see some example, and then finally we say that if our big X of z is rational, then ROC is bounded by poles or infinity. And so if you are rational and right-sided, then ROC is outside of the outmost pole, and then it's equal infinity if only if our signal is 0 for n less than 0. And similarly for left-sided signal, ROC is inward and equals 0 if only if our signal is 0 for n greater than 0. Okay. And then we see that there are three ways to do inversely transform. There is this brute force integration. If you want to do integration, you fix the R inside ROC and do this integration of omega from 0 to 2 pi. And also you can do partial fraction expansion. And here, quite importantly, you want to expand in terms of polynomials in z-1, because our corresponding example 10.1 is this function that's written like fraction, partial fraction in terms of z-1. It's 1 over 1 minus a times z-1. Okay, so you want to do partial fraction expansion in terms of z-1, get this. And then with a different ROC, you will pick whether each partial fraction will inverse transform to a right-sided signal or left-sided signal. And if the ROC is outside, you transform to this right-sided signal. And if ROC is inward, then you inverse transform to this left-sided signal. And finally, in method 3, we see that sometimes you can do power series expansion and just look at this formula to directly invert your Z transform. Okay. So we see that if you are already in this power series of Z, then you can just read x over n by this correspondence. So d to the n0 will inversely transform to delta of n plus n0. And but sometimes your signal was not in direct power series, then you need to be creative to get into a convergent power series of Z. Okay, so for example, this 1 over 1 minus a to a Z, 1 over 1 minus a times Z minus 1 can invert to two different power series depending on your ROC. It's either this power series in terms of AZ minus 1 or this power series of A minus 1Z. Okay. And also we see that even we have a non-rational function, so we have this log function, then we can smartly choose our power series expansion. So this time we expand in terms of AZ minus 1, and then we use this Taylor series expansion of log 1 plus b. And once again, we get a power series expansion of x of z, and we can get our x of n out here. And yeah, then finally we have some geometric interpretation of our Fourier transform from the point 0 plot of our Laplace transform. Z transform. Okay. And yeah, next time we'll start properties of Z transform, and maybe even a bit, yeah, we'll start down here, and we can see where we can get. Okay, so see you on Thursday.